Hello, everyone. It's a pleasure to be here on GeeCON for the second time. Last time I've been here 2 years ago. And I'm also happy that this conference is thriving in Krakow because it allows us to kind of expand our horizons as software engineers. Today's presentation will be kind of abstract. So I'll try not to bore you to death. There won't be much code examples here, but rather concepts that apply to our everyday's work. And we'll be talking about models and complexity, which in essence are one of the most misinterpreted concepts in software, the same way as quality and architecture and a few others. But before I start, I need a little bit of an assistance from one of you. So can I maybe ask you just I won't ask you to the middle of the stage. Can you just draw a car for me in like 30 seconds?
What kind of car? What capacity? For people or cargo?
Let it be cargo.
Cargo car. Like city cargo car.
Yeah, sure. And thank you very much for assistance. In the meantime, a bit about myself. I'm from the city of Łódź, home of another great conference about mobile software development called Mobilization. I love GeeCON. I've been attending GeeCON before it was cool. Actually, it was always cool. And my main battleground is financial technology domain. Mainly, that's my favorite, mainly because it deals with the complexity, but not only a level of hardware. The problems out there is not as much scalability and trying to develop great distributed systems and so on, but it's rather the people's understanding of the financial domain and trying to grasp the complexity of how financial institutions operate. And that's fascinating because that's something that hasn't been solved, and that's why probably startups in this area emerge so frequently, because it's so easy to start from scratch, because all these large financial institutions are dealing with the problems of complexity they've introduced to their organizations long time ago. I worked at LandUp. It's a consumer financial technology startup in San Francisco, and it's an awesome company because I think it's the first company I've worked in that actually helps people, and not in a way that you are helping gamers have a better real-time experience, but really providing them with access to financial products that otherwise they wouldn't have it. And my Twitter handle is also here. So in case you were planning to leave early or fall asleep in 5 minutes from now, I just want to convey this little message. Domain-driven design, test-driven development, solid principles, which are also called object-oriented programming, but I'm not using this concept because it's very overloaded and it's got somehow bad reputation. And functional programming. If any one of you doesn't know at least one of these concepts, please learn them before you start coding. I'm surprised that we've been through software is 50 years now, and these things are not taught well at universities. So models. Can we see that car? Yeah, I don't know if I'm able to kind of show it. So I'm just gonna show it for the prosperity here. And there's a smaller version of a car here, right? Scaled down. The bigger one, right? So generally, we see an object here, and what can we say about it? For example, if I ask how many wheels does a car have, and if we look at this drawing, one could actually conclude that it has 2 wheels. But on the other hand, intuitively, it does the job, and I'm happy that you actually asked what car should you draw, because this is exactly what I want to talk about. So this is a model of a car, and for the purpose that I've asked for, this model does very well. It represents a cargo car, a kind of a European-style cargo car, I would say. And there are lots of models of cars. The one that you see right now is what you would call schematics. And what does this particular model convey? It shows us proportions in details that are sufficient enough that you could probably put it in some software design tool and have a 3D model of Chevrolet Corvette. Or you could actually build a chassis of such a car based on this model if it actually had dimensions plotted on that. It's also called, it's called blueprint, right? But this is also a model of a car, although it's very different, one would say. For instance, it does have 2 wheels, or at least it shows only 2 wheels, although our intuitive understanding of a car is deep enough, engraved in our brains that we know this actually has 2 more wheels on the other side. And what does this model of a car convey? That, although it's so different from the other one, this one shows us the dynamics of the construction. It gives us this intuitive feeling of a sports car. It is probably designed. This has probably been drawn as one of a series of concepts of some particular car, in order to come up with a design that's a pleasure for eyes and that would sell well. If we were to build a car based on this drawing, we would fail miserably, because it doesn't have well-preserved proportions. It's got some perspective. It doesn't have enough details to do anything about that, and so this is definitely not the right model for car. On the other hand, if we used the blueprint of a car just to try to discuss various options of design, we could say that this one is too concrete. It expresses too many details which are not relevant, and probably it makes the discussion about a design of a car less useful. And we actually have an analog of that in software world, which is, you might be familiar with the concepts of wireframe and a mockup, where a mockup is a more concrete implementation of a design of a web page or a mobile app, while wireframe is something that is specifically designed to only talk about placement of various fields and a feeling of whether we are going the right direction, and not be concerned about colors, fonts, and rounded edges. So yeah, next time I ask you to draw a car, what will you ask of me? You already asked that, so it's not a mystery. For what purpose, right? And then we could come up with a model that fits this purpose. And we could, let me just quickly go through examples of models from science that to some extent describe the similar concepts, but serve a different purpose. And here you have a standard model and a chemical table. And the first one is great if you are talking about quantum physics, but it would probably be a total like a lot of overhead to use standard model to talk about chemical reactions, although theoretically it would be possible. Now, which one of these is the realist, one would say? The standard model is definitely closer to the truth, but on the other hand, it's neutron or like muon more real than helium. I'm not sure. I haven't seen any of these. What about the simplicity of a model? Does it matter? Here you have the supergravity equations for 11 dimensions, and here you have the gravity equation from the field theory that to some extent they overlap. They can be used to describe similar concepts, and just by looking at the amount of equations that is needed here, you might say that a field equation is easier, but it's actually the context that you'd need to know to be able to say that for sure. And the other one is where we have a well-known Newtonian gravity at the top, and what do you call it? Relativity theory, adjusted gravity equation. Well, obviously, Newtonian equation is simpler, and you could use it to fairly well describe the forces acting on an elevator, or even they work well enough that you could probably use them to build airplanes and to make sure that airplanes actually are able to fly. But if you want to describe the motion of bodies that are very close to a black hole, you would probably get too big of errors there. And I would like to introduce you to a concept from a great book by Stephen Hawking and Leonard Mlodinow, The Grand Design. I think that's Hawking's last book. He passed away. Mainly, it's called Model Dependent Realism. So they argued that we can only interpret reality based upon models. And if we have a few models that describe certain phenomenon well enough, then several equally valid realities exist. So we can kind of conclude from that that the reality itself is not really useful to talk about in a scientific word. It's the models that matter. And you can say that the model is a simplification of a reality, that in particular bounded context, it is a reality. So take an example of that concept of a car. Maybe that car will never be drawn. Maybe this drawing does not represent any existing car. What does it mean? That the car does not exist, that it's not a car? It is a model of a car, and in the context of design, it is a car, right? And so think of an example of, maybe let me come up with something more ridiculous. Like, for example, Tooth Fairy. There's this U.S. Kind of tradition that when kids loses a tooth, they put it under the pillow, and the next day they find $1 under a pillow, or maybe right now it might be $10 or 100 in Silicon Valley, and Tooth Fairy is a valid model. It represents an operation that changes a tooth into dollars. And just in this narrow context, it's actually a valid description of reality. It doesn't really matter if anyone saw a tooth fairy, right? Although we all know it's not truth. So now let's go back to software. This is the citation from 1958 when the term software was used for the first time. So John Tuckey has written, "Today, the software comprising the carefully planned interpretive routines, compilers, and other aspects of automative programming," sorry for reading, but I wanted to have it right, "are at least as important to the modern electronic calculator," which we call computer these days, "as its hardware of tubes, transistors, wires, tapes, and the like." So let's, for a second, let's look what is the difference between these two groups of concepts that John Tuckey has mentioned here. The compilers versus transistors. Obviously, the second group is physical. You can touch them. You can touch a transistor, you cannot touch a compiler. And if you think among these lines, almost all the concepts that we as software engineers are dealing with every day at our profession do not exist. They're abstract. They are actually models. So monads, if you hear about them, they don't exist. And neither do objects, functions, threads, and so on. But what does it matter? So once we realize that all the constructs that we are dealing with are not fundamental to computer, then you might ask, what are they for? And I hope we all know that they've been developed. These are the abstractions that have only been developed for us to communicate better. And this is something that we as engineers tend to forget. So we started talking about abstractions. Let's go a little bit deeper into that topic. So as we said, most of the concepts we are working on from the software engineering world are abstract, and they're actually built on top of what we call an operating system, and on top of actually specific operating system that is called Unix, as was specification, I mean. And so we can say that Unix is a very useful model for software engineers. Now, how do abstractions emerge in a language? So let's go back to human language for a second. And let's think how human language actually has evolved. So you can imagine there were a group of primal Homo sapiens in caves that have just learned to articulate syllables. So they were just pointing fingers at things and vocalizing these syllables. And they were pointing at one thing and called it fire. They were pointing at a person and call it a man, a woman, a child. Or on a sharpened stick and call it a spear. These are concrete concepts, or we can, using programming jargon, we can say these are low-level concepts. And then what happened? They wanted to be more expressive. They wanted to talk about more sophisticated things. So they pointed at the group, a man, a woman, and a child, and they called it a family. And they pointed at a few people running with a spear after a mammoth and called it hunting. Or a tiger eating a person and call it danger. Because of that, we are probably here, because otherwise, it's easier to just scream danger than a few other syllables that would mean, you know, life or death. So let's go back to modern times, and this is to define this concept. Why do we even need abstractions? So you see this guy. He's probably has, I don't know, 2 minutes to explain to the team the strategy for the remainder of the game, and he has to do it effectively. So if you heard what he is saying, although it is English, you wouldn't probably understand a word unless you are a big fan or professional basketball player. And this is just a short list of basketball tactics that this is just the beginning of a list of basketball tactics that are used during such sync-ups. So you can say that he is speaking a domain-specific language that is built on top of a general purpose language, which is English in this case, and he must be doing this very effectively because it led warriors to victory. Now, another example. So let's have a few definitions. We have a star, which is self-luminous gaseous spheroidal celestial body, a planet with its own definition, asteroid, comet, orbit, and the last definition is periphelion. Sounds simple, point in the orbit closest to the star. But if we were to inline all these definitions so that periphelion is expressed in only low-level terms, we would have this sentence, and I'm going to read it. Periphelion is point in the elliptical path of a round celestial body which has removed debris and small objects from the area around this path. This is the constraint that actually makes Pluto not be considered a planet. Small rocky celestial body or celestial object consisting of a nucleus of ice and dust closest to self-luminous gaseous spheroidal celestial body. Now, you can, I hope you can already observe the complexity that such a low-level communication introduces. And this is why we need abstractions in the everyday language that we speak, but also in software. And then you might think, is it really that abstract? It kind of is. All these terms that you see here, they don't have a physical manifestation. They are just there to help us write better software. So, and I'd say that there's been titanious amount of work early during the emergence of software engineering discipline to deliver these abstractions so that we can use them to program better, to have operating systems, to have general purpose languages, to have frameworks, and a lot of tools. And what have we done with that? At least from what I observed, we kind of tend to not continue this trend and be a kind of ultimate roof that lays down a mess on top of beautifully designed abstractions in software system, and it's not deliberate. This is more due to the way we organize ourselves than us not thinking about something. But to be honest, there's still a fairly lot to do within the abstractions that are provided for us. So this is an abstract representation of let's say a dynamic language or even a static language, a function. So we have type V. We have a function that accepts a structure of type V and returns a structure of type T. And there's there are implicits all over here. We don't know if this function takes time or not. We don't know if we need to do a null check here. We don't know if it can mutate the input, or does it require global state, or can it throw exception? Who knows? So, and there are actually languages that allow us to introduce these constraints better, and I think software evolves towards that direction to be more explicit about these constraints. So, so this is also, this is abstract. This is not from any particular language, but maybe similar to something. So here, let's say that that this kind of arrow that we see here means that this function is not allowed to have any effect. Let's say the future type says it can take time. You need to be able to wait. The try construct says this can fail. You have to be ready for that. And also the input, you see that it's not only it accepts the input parameter, but it also accepts the context, which represents all the dependencies that this particular function may need. And this is a great quote from a book called Understanding Software. Fairly recent book. I would advise anyone to read that. A lot of good concepts. The world of computers is full of things that should have been strict from the beginning and became ridiculously complex because they were not. So you start to see this, you know, this how this terms of abstractions, constraints, and complexity start to work together. Now, question is, and that's an example from another book that I want to provide here. Can we over-constrain? Is there a limit on the other side where we introduce constraints that are too tight in order to do something useful? And there's this example from this book that touches the concept of complexity on a more general, in a more general domain. Is that they had an experiment? They developed a method that that can statistically come up with mixes of drugs that are effective for curing cancer. And so they had two drugs that might be very effective for cancer cells during the cell division of that cancer cell. So if you add to those two drugs a third drug that promotes cancer cell division, which is ridiculous idea to add something that to the mix, because you just speed up the cancer development. It might be a good thing to have. But if you constrain your mixtures that they should never even, you know, contain something like that, then you can say that we have over-constraint. So the question to all of us is, what abstractions have you provided? And then you might ask, well, what do you mean? My clients are not programmers. Why would I provide abstractions for them? It's like we are the buck stops at us. We use the language and we build tools. But on the other hand, if you think, there are languages that have been successfully developed for non-programmers, you might say. And my key example is SQL. This is one of the most, or maybe the most successful domain-specific language, because it's the way that it hides irrelevant details, the way it hides temporal coupling and being purely declarative, it's fascinating to me. And also, like, when these people have been developing SQL, I don't think they could even conceive the scale at which it will be used. And there were lots of rants against SQL, you know, no SQL. I know how it ended, but every company I worked in still uses SQL. So and the other example that I recently came across is the Facebook's GraphQL API. There's a kind of a equivalent of SQL in the API world, and this is I was very happy to see that something like this is happening, and we actually at LandUp started using GraphQL for our mobile development. And what happened is that our product managers started to test our software with us by using GraphQL queries. This is something that would never happen if we just exposed REST interfaces, or to be less strict, JSON over HTTP. Now, so here is a typical stack. We have business, software, and hardware, and we tend to this stack is probably developed. It's been developed as a metaphor from civil engineering, and we tend to do this when we don't have good metaphors. We try to borrow them from other industries, and it's not necessarily ending well. So hardware is kind of, let's leave that for a second. Let's zoom in on the business versus software. The model is that the business provides the instructions on what to build, and the software knows how to build it, so they deliver. And what often happens is that there's a lot of miscommunication. And why that happens? So this is a model. Let's remember that from the beginning of this talk. It is not a reality. And this boundary is artificial. The boundary between business and software is a model, and that model may actually be wrong. So we could draw the different spectrums or dimensions here, but if you look at the tendency here is that at the boundary between hardware and software, the physicality ends. And at the boundary between software and business, the formality ends. And what formality means is that above this level, we cannot formally prove that something is right. And it is not very good. So what tends to happen is that we introduce, the companies, the organizations introduce another level between business and software and call it product. So you can say we just introduce additional layer here to make this transition from formal to very informal descriptions smoother. Product can come up with models that are semi-formal, specifications, user stories, UML diagrams, and so on, that help a bit, but fundamentally we are still dealing with this boundary. It doesn't help. The formality ends here. We still would not be able to prove that something above software actually works. So zooming in on this boundary, how engineering communicates with business, and I've listed a few concepts that are used within these domains. I hope they're generic enough so that you can all relate to that. And user, account, customer, hands up who in their systems, in their code base, have a user class or user object. Quite a lot. So looks like there's something generic here. What about account class? Still a lot. See, so there are some models that we can come up here. And how do we? By the way, this might be good. This might be bad because there is a phenomenon that I've already seen twice. Oh, third thing, product class. a bit less. So watch out for product class. This is super dangerous because the interpretation of product is so it's so confusing to different domains that you can come up with, that you can have a product class, but it will actually mean different things for different people. It could even mean different things for different developers, and when that happens, you end up with hot mess. So what means do we use to communicate between these boundaries to make it better? We use experiments to prove some business theories. We write specifications, UML diagrams. We have data schemas. Some of them can be understood by non-technical people. We talk about tech debt to justify refactoring. Or we can go further and develop domain-specific languages. But the direction here is something like that. When engineers want to describe something that is concept from within the system, we tend to use metaphors because metaphors have this ability to relate to concepts that people are comfortable with and hide irrelevant details. And in certain very, very narrow contexts, metaphors are the right models. And on the other hand is when we get specification as engineers, what we would like to have is something that is as formal as possible, something that we just look at it and we develop software, and that's it. Maybe a little digression about tech debt. Tech debt is a good way because it triggers people's thinking about, are we in debt? It means that we owe something. Then we cannot just decide not to pay it back. It's just a question of when. So this is the power of this metaphor, but it also has its drawbacks because. I will not go into details of that. That's maybe for another talk. But I wanted to point out the last medium of communication, which is domain-specific languages. This is something that has these traits of both being a good metaphor, because domain-specific language describes our system in terms that business people understand, but it is also formal. It can be proven. It can be, you can write unit tests for domain-specific languages. So you see that this is one of the things that actually that actually builds abstraction on top of the language that we use and propagates this language as a tool for the business to build something. Now, complexity. I'll try to rush. So this thought: if a delivery speed of a system always decreases, we know all that stuff, and that's probably because complexity of a system always increases, and from the thermodynamics we know that entropy of system always increases. So there's a lot of people try to, at least people who had some like physics courses, try to relate these concepts. And Norman Ralph Augustine he's like a aeronautics. He used to be an aeronautics entrepreneur, and he has this list that is called Norman Augustine laws. And law number 17 states that software is like entropy; it always increases. But the question is whether it's good to actually talk about complexity in relation to entropy, because entropy is about particles moving in a container, and in software there's really infinite number of forces that act upon the system, and the components of a system are not self-similar. So it's really probably impossible to come up with a formal model of software as an entropy. And these metaphors from physics are very compelling, if you think, because if someone managed to achieve a model that uses some physical equations to to describe a software system, we could then prove it. And it's very compelling. But in most cases, it's actually not doable. So let's go back to something concrete. Like, for example, cyclomatic complexity, which is formal. It's the McGabe's definition. So, we have number of edges in a flow graph, number of nodes, and nodes that have exit points, and we just have a calculation, and people have, there's been some deficiencies identified with this model. So Sonar Cube group has developed something on top of that, which is cognitive complexity. It's McGabe's cyclomatic complexity with a few more constraints that can fairly well describe the cognitive complexity of a method or a function or a class. So what's the problem? Let's just take this definition and scale it to the system level. I looked actually that might be a compelling thing. So I looked a bit over the internet of whether there's been some initiatives to do exactly that, and found this paper fairly recent, March 2016, where they concluded that at a system level, the complexity has very significant subjective components that you can really that are very hard to model. So, and then again, cyclomatic complexity, it only indicates the complexity on a unit level. What about the structure of units? And there are also there's been initiatives very interesting. These ones are by Edmund Kewan. They're called Spoiling diagrams, where you can draw graphs of components in a system, be it like classes or Java packages or whatever. And there are some patterns that you observe that could identify good or bad design. And another one, this one is Structure 101. It's a tool, I believe it's available for Java and .NET to actually measure some kind of complexity of the whole architecture of a system. And for some reason, unfortunately, this didn't get a wide recognition. Although I also found this, that if you use a proper model, in this case, this is like the circle of dependencies. A few independent architects in our industry has suggested that this is very useful to break up monoliths into microservices. So you draw this diagram, you look at the dependencies, and you kind of collapse the components that are very tightly coupled together into a microservice. Haven't tried that myself though. Again, what's the problem? The structure only indicates the complexity at the system level. So what about how the system expresses the business idea? And you can see this this recursive pattern here. So if we see recursive patterns, what do we draw? A pyramid. And the pyramid, so what can we do? We can have wrong code, we can have wrong specification, or we can have wrong idea. What we as engineers tend to focus on a little bit too much is how to deal with wrong code. But there are certain processes and initiative that try to deal with the wrong specification, but the wrong idea is something that's still at the discovery level. And so what if we write good code for the wrong specification? It's probably better to have good specification with wrong code. And similarly, what if we have perfect code, perfect specification, but there's a wrong business idea? This is a lost effort. So one can say, what's the problem? Let's just write better specifications. And the PMs can say, well, how about you have 100% test coverage? And that's not, this is this boundary, this is this wall that I was talking about. And this is something that we should consciously try to break. and a quick manual of how do you build a wall in organization if you want. I don't advise it though. You just get a group of people, sit them together, give them a name, and just watch the wall grow around them. And I've seen this pattern too many times, where you have, for example, a DevOps organization, or UX organization, or a quality engineers organization. And to have a project that involves this organization, it requires so much coordination that it's effectively like a lost cause. So let's, break the walls. And how do we do it? How can we, as engineers, help the business to validate the idea? And so again, it's simple. Allow them to experiment. Allow them to choose. Do A/B testing, canary deployment. To give the business power to choose between features. Let deployment of features be easy enough so we can test whether control group or experiment group performs better. How do we turn idea into architecture? There are also plenty of ways to do it. The one that I recently am evaluating is domain-driven design and related concepts like event storming, where you come up, first you do event storming, you come up with domain model, you turn the domain model into some executable specification using behavior-driven development, and then you can develop architecture, beautiful architecture that is not that does not involve any useless concepts. And if you ask how we write better code, this is not something that I want to talk about right now, because there's plenty of experts on that have, and a lot of good books. But we still have not defined complexity. So what is a complexity? If there was an ideal solution and our solution, the complexity could be the distance, the Euclidean distance between the two. But the ideal solution, it's like, is there an ideal solution really? It's a moving target. And if we cannot define it, if we were able to define it, we would build it. So might not be very useful. So another thought. There are certain complex concepts that are still kind of provable. Calculator, Git, Postgres, Linux, linear time, shortest path first. And there are others, like getting people to the moon, cure for cancer, fixing financial problems, or coming up with a decent web application. So the difference between the two is, although both are complex, the second group involves a lot of interaction with people, and people tend to be dynamic. The concept of gaming, fog of war, you only see topology, but you don't see what is happening behind the fog of war. You don't see units moving there. So you cannot make very useful assumptions. Henri Poincaré was the first to define something that's called deterministic chaos. It means that if you have systems that are where a lot of components are dependent on each other, a tiny change in initial condition can result in totally different systems. So, which means that you can have a deterministic system that cannot be predicted. And formalism. So I think that's the last concept that I will describe, because we have, 5 minutes right now? Or 40 seconds, sorry. So if we have cash and we want to come up with a cure for cancer, it's not only the cash that we need. We need the whole context: technology, people, knowledge, and communication. So let's group it together. Why don't we just call it context and put it as an input here? But this is actually the thing that I described, because these inputs have so much dependencies between each other that effectively you cannot just treat them as single value. And that's the last thing I wanted to maybe convey as a takeaway from this presentation. It's not the way things are in software that are complex. It's the way how do we choose to speak about them. It's the language that we develop. And that language is something that we do have control on. So let's not just try to deliver tools for the business. Let's try to deliver languages for them. So, you know, the metaphor with the fish. Give a man a tool, and they will have a tool, and maybe they will be able to solve one problem. But if you give them a language, if you think more about domain-specific language, if you explore the business domain that you are dealing with, and codify it, and allow your clients to actually use this language, then you will watch them solve their problems for themselves. And that's probably something most rewarding to a software engineer. And yeah, with that, I would like to thank you, and I hope you get something out of this talk. Thanks very much.